Hey guys, how's it going? Day 14 here, last second video before you guys take the test tomorrow. Hopefully you're studying, you're ready to go for this. I wanted to go over a couple of problems about continuity just to refresh ourselves. So these are three problems from the review sheet that sometimes need a little extra clarification. So the first problem here is f of x is this piecewise function here. We have one function defined for x less than 1, one function defined for x equals 1, and one function defined for x is greater than 1. The question is x continuous at x equals 1? Well, again, to prove continuity, any question about continuity, we want to go through those three steps. Step 1 being the limit exists, step 2 being the function is defined, step 3 being the limit and the function are equal to each other at that point. So to start this thing, we want to start with step 1 and show that the limit exists. To show that the limit exists here, since 1 has a different function for less than 1 or greater than 1, for x less than 1, x greater than 1, we want to look at the left and the right-hand limits. What I really need to see tomorrow, when you come to a problem like this, I need to see the left-hand limit notation and the right-hand limit notation. I need to see this. So I don't want to just see 3 times 1 cubed minus 5 equals negative 2. I want to see the notation that says the limit as x goes to 1 minus of f of x equals that. We need to make sure that when we're doing a left-hand limit, we're plugging in where x is less than the point. So we can see here that the left-hand limit is negative 2. We also need to show the notation for the right-hand limit. If you do not show that left and right-hand notation unit when you need it, like in this problem, you will not receive full credit. So it's really important to make sure you got this down. So again, don't just plug into both and get negative 2 and just write that. You need to show me the notation. Limit x goes to 1 minus of f of x equals negative 2. I need to know that you're plugging into the correct one. Limit as x goes to 1 plus of f of x. We plug into where x is greater than 1. And we also get negative 2. And I need to see a third step here. Because we know now that the right and left-hand limits are are the same, then we know the limit as x goes to 1 is equal to negative 2. This does not mean the function is continuous. This means that the limit exists. We passed step 1 in the test. Now, if we go on to pass steps 2 and steps 3, then we know that the function is continuous. If we fail either step 2 or step 3, we know that the function is discontinuous at 1, and we also know, because the limit exists, we just showed that, we know that it's a removable discontinuity. Okay, so let's check step 2. Step 2 is about, is our function defined at 1? And the answer is yes, our function is defined. For the actual value where x equals 1, we want to use up here. When x is 1, our f of 1 is negative 6. Okay, so we passed step 2. Step 1 was passed, step 2 was passed. Step 3 says, does the limit as x goes to 1 of f of x equal f of 1? We can clearly see here that they don't, but I want you to write the notation that shows that. Right? The limit as x went to 1 of f of x was negative 2. F of 1 is negative 6. Therefore, we know that these two things are not equal to each other. Therefore, now we can say, therefore, f is discontinuous at x equals 1. So we know that it's discontinuous because we failed step 3. Because we passed step 1, we know that the type of discontinuity is removable. So we know it's a removable discontinuity. Let's take a look at another problem from the review sheet. Here we see that f of x equals x squared minus 25 over x minus 5 for all values of x except x cannot equal 5. Sometimes students get a little bit confused about this notation here, that this x does not equal 5. That means for any other number, 4, 6, 100, negative 30, we use the function x squared minus 25 over x minus 5. The only place that we do not use that top function is at the value of 5. When x actually equals 5, we use k. And this question is going to say, what value does k have to be to make f continuous at x equals 5? So what should k be? Okay. So to solve this problem, again, we want to go through our 3 steps for continuity. So our first step is the limit. And again, I don't want to just see you do x plus 5, x minus 5, cancel out the x minus 5, and just write 10. I need to see the notation of what you're doing. This is really, really, really important for graders on the AP test. Obviously, except for on multiple choice problems, you just need to get the right answer. But we want to practice good notation to make sure that we earn all the points we can on this test. And it'll help us understand what's going on a little bit better. Okay, so first we need to find the limit as x goes to 5. Well, to calculate this limit, I'm going to do it differently than I did in the problem before. Because the problem before, I had a different function defined for when x was less than 1 and when x was greater than 1, I had to do a left and a right-hand limit. In this particular problem, the left-hand and the right-hand limit, right, numbers a little bit less than 5, numbers a little bit greater than 5, both apply to the same function, x squared minus 25 over x minus 5. So, and again, since limits care about what's going on around the x value as we approach 5, it doesn't care about what's happening exactly at 5. We want to use the top function, x squared minus 25 over x minus 5. When we take a look at this problem, we see whenever we have limits, first thing we want to do is see what happens when we plug in the number. Well, when we plug in 5 here, we're going to get 25 minus 25 on top, which is 0. We're going to get 5 minus 5, which is 0 on the bottom. So we get 0 over 0, right? But never fear, limits deal with 0 over 0 quite well. One of the methods that we can solve this problem is by factoring. If we factor the top, we can see that it's a difference of squares, so we can break x squared minus 25 into x plus 5, x minus 5. Right, that's going to allow us to cancel out that x minus 5. So we get simply that our limit as x goes to 5 of f of x can be solved by using the function x plus 5. Now all we have to do is plug in 5 for x, and we get 5 plus 5 equals 10. So we know that the limit as x goes to 5 here of f of x is equal to 10. Okay, so we showed that the limit does exist here. Therefore, it's going to be possible for us to prove it's continuous, right? We just have to think of f of 5, right? F of 5 must be defined. Right now, f of 5 is defined as k. We want to know what should k be so this thing is continuous, right? Think, if k was 6, f of 5 would equal 6, but that wouldn't equal the limit as x goes to 5 of f of x. Right? We want to choose k so that f of 5 equals the limit. We want f of 5, that must equal 10, so that the limit and the function are equal to each other. Therefore, k must equal 10. Next. Here we have a function where we see we have, for x is less than 1, we follow the function 3ax squared minus 5. For x is greater than or equal to 1, we follow the function 2x plus 6. The question is, what value a makes f a continuous function at x equals 1? Once again, we need to consider the limit. Now here we have a different function for x less than 1 than we do for x greater than or equal to 1. So we're going to have to show that the limit exists here. I need to show that the limit as x goes to 1 minus of f of x equals the limit as x goes to 1 plus of f of x. I already know that f is defined at 1 because of that little equal sign down here. This little equal sign right here tells us we use this function for f of 1. Right away, we know that f of 1 has to be 2 times 1 plus 6. So f of 1 has to be 8. So we already know that. But what we want to show here then is we just want to make a variable. So, a is a constant. We want to choose a so that the left-hand and right-hand limits match. So what we want to do is say this. Right, we are plugging in 1 into both functions, and we want to make sure that they equal each other. Right, so we're plugging in 1, but we're plugging it in for x. I saw some people in class were plugging it in for a. Right, we don't know what a is going to be. That's what we're solving for. We want to plug in for x and now solve for a. So when we go ahead and do this, we can simplify this. 1 squared is 1. 1 times 3 is 3. So we get 3a minus 5. Equals 8 when we simplify the other side. When we add 5 over and divide by 3, we get a equals 13 thirds. And when a equals 13 thirds, that will make this function continuous. Okay. The last thing I want to talk about is what we need when we do the IVT. Just a reminder, this is in other videos, and if you want a bigger description of it, you can search up the video on the intermediate value theorem. But just as a reminder, here's what we need. In your explanation, part 1, you need to somewhere in there state that the function is continuous, right? So even though it's stated in the prompt, you're going to need to state that in your explanation. That is a condition that must be present for using the IVT. You also want to state the 2 values that surround the C value that we're looking at. So you want to state that f of a value and that f of b value to show that the f of c value or r of c value that you're looking for is in between those 2 numbers, right? Then the third thing you must do is you must, your reason must state that it's because of the IVT. Okay, so those 3 things need to be present. I'm going to be looking for all 3. If you don't have all 3, you will not get full credit for the problem. Okay? Study hard, be prepared. I can't wait for you guys to show all your knowledge tomorrow. Sleep well, study hard. Peace.